Hello. So in this video, we're going to talk about Haberman's section 4.2, in which we derive essentially the wave equation for kind of a vibrating string. And so the punchline will be, well, what does the wave equation look like? One form of it takes this form, where we have rho naught being a mass density for a string times the second time derivative of the height of the string u. This is going to be spatial derivative times t0 du dx, where t0 represents something like the tension forces in the string. So we're taking one spatial derivative of t0 tension times one spatial derivative of the height u. And then we also have some black box term, some source term for any other forces acting on the string. Okay. So this is one form of the wave equation, right? It tells us how a string vibrates using properties of kind of the mass density of a string as well as tension and other forces. If we assume that all of these constants, so rho naught and t naught, are constant, as well as if there are no source terms, right? So q is 0, then we get kind of another form, or slightly simplified form of the wave equation that looks like this. Okay. Where now c squared is equal to t0 divided by rho 0. So the goal of this section is to just say, right, where these equations coming from physical principles. Okay, so in deriving the heat equation, right, kind of the main piece we used was this sort of conservation law, where we said, well, let's take the total thermal energy in kind of a region we care about, and then let's see how that changes. That depended on kind of the flux across the boundary. And then we had Fourier's law that said, well, flux is proportional to the temperature gradient. And then put all these pieces together, right? We get the heat equation that has one time derivative and two spatial derivatives. The derivation for the wave equation is actually going to take a very different, or use a very different sort of set of physical principles. In particular, we're going to be using Newton's law instead of kind of that other conservation law and Fourier's law, right? And so recall that Newton's law says, well, if you have a particle that's moving around in space, right, the question is, right, how do we describe the motion of this particle? And so Newton's law says, well, right, the motion, which we get from kind of the mass of the particle times the particle's acceleration, right, mass times acceleration is just kind of the cumulative forces acting on the particle. Okay. And so in deriving the wave equation, we're going to be using Newton's law. And so already, right, we can see, well, maybe this is where we're going to get the two time derivatives instead of just the one time derivative, because we're going to be looking at some sort of particle associated with kind of the string. And we're going to be looking at the acceleration of that particle, which has two time derivatives. Okay. And so as the second line says, yeah, what we'll be doing is kind of approximating, this continuous string that we may be interested in as like a series of particles kind of stringed along, you might say like a string of beads. And then we'll be looking at the motion of each of those beads and then take some limits, yada, yada. We're going to recover the wave equation. Okay, so let's see how that goes. So let's draw a picture. So kind of the setup that we'll be doing is the following. So take us kind of fix a horizon, right? So this line is going to be height equals 0. Okay. And so then what we're going to do is we're going to say, well, suppose we have a vibrating string. Okay. The height of the string is going to be the function we care about, where you plug in an x value and you get the height of the string above that x value. So then this might be x equals 0 over here. Over here, this might be x equals L. Okay. And so kind of the function that we're interested in is going to be the height of the string at any given x value. And the question is, how does this height change in time? Okay. So one kind of assumption we're going to be making is that take a portion of the string. The motion of the string is completely vertical, right? So fix a point, right? Fix an x value, look at the corresponding section of string. It's only going to be moving it up and down, which you might say, well, of course. But kind of in practice and physically, what tends to happen is, right, if you have a string that's vibrating or kind of, moving around, if you look at two pieces, two kind of tiny segments of the string right next to each other, as one segment kind of moves up, that's going to pull this other segment with it. And then this other segment might go below kind of that portion, right? So in practice, right, if you have a string and you kind of like wiggle it around, you might get some sort of, you might say like cusps or portions where the string folds over itself, even if only a tiny bit. We're going to say for kind of the derivation, we're going to assume that doesn't happen, right? Maybe the scale of these vibrations is small enough so that we can approximate the motion as being completely vertical. So, okay, and so kind of how I've been saying this is, well, we're going to approximate the string by, kind of string of particles or like beads strung up against each other. Maybe a slightly more physically, you might say, I don't know, robust way of saying this is, well, if you zoom in on the string, in practice, what we're going to do is we're going to say, well, let's look at a tiny portion, tiny segment of this string and see what the motion is like. So we're going to kind of take this segment small enough so that this whole segment moves as one body. Okay. And of course, to describe the motion, we need some notion of kind of mass for the string and things like that. For a mental picture, you can say, well, right, whatever's happening with the segment here, let's just say, this segment behaves like kind of a single particle, where the mass of this particle is the mass of this string segment. Okay. And so then that way, right, what we're going to do is we're going to say, well, cut the string up into a bunch of these tiny little segments, and then take the mass of each of those segments and just associate it to that particle. And then that's going to get us kind of the string of beads that I've been talking about. Okay. And so then to describe the motion of the string, and what we're going to do is describe the motion of each of these particles and then say, well, let the width of these segments go to 0, so that you kind of fill in the space, and you're good to go. Okay, so I've been talking about the mass of each of these segments being associated to these particles, and so the question is, okay, well, where are we getting the mass for the string? And that's going to come from these other functions that we're going to associate, where we're going to have this mass density, right, there we're associating to the string, and kind of set things up in a way so that the mass of kind of particle or the mass of a thin segment is going to be this quantity, where you take this mass density, right, and then multiply it by the length of that segment. Okay, so looking at these things, this mass density, this should have units then mass per length, right? Because then here we're multiplying by kind of a segment of length to get mass, but anyways. Okay, so this is kind of our setup, and right, how we're going to set things up to use Newton's law to describe the motion, where we're approximating our string by a bunch of these little tiny segments and thinking of these segments as particles, and we're going to describe the motion of these particles. So the acceleration for each of these particles is going to be the mass of that particle. So the forces acting on each of these particles is going to be mass times acceleration. So that's one side of the equation. Now what we need to do is go through and figure out what the other forces acting are. Okay. Okay. So, right, what are these other forces? Right. Well, of course, gravity may be a thing, depending on the scale of the string and kind of the vibrations that you're looking at. You might say, like, depending on certain physical properties of the string, gravity may or may not be a concern. But generally, gravity can happen. The other forces that will act on these particles and kind of is present within the string is going to come from tension in the string, right? Or kind of from our setup, you could say, well, these other forces are going to come from how these particles are pulling the neighboring particles. Okay, so let's draw a picture. So let me draw it like that. Maybe this is a thin segment. Okay, and so this is our particle right here. And maybe we have two other particles. So like one right there, one right there. Okay. And so the claim is, right, some of these other forces that are going to dictate the motion of this segment are coming from tension. What is tension? Well, tension is going to be the forces that the string feels at its endpoints coming from how the other portions of the string are pulling it. Okay, so here we're going to describe this tension using this vector t of xt. Okay, so here we're going to call this point x. Over here, what is the x coordinate here? Well, this is going to be the x coordinate x plus delta x, this infinitesimal segment. So then this vector up here is t of x plus delta x, right? X plus delta x is where we're evaluating this vector at time t. And then down here, this vector is just t of xt. Okay. So we have these tension forces, right, that are pulling this particle. But again, our assumption is that motion is just vertical, right? These particles are just moving up and down and not horizontally. So what we need to do here now is say, sure, these are the vectors that are describing these tension forces, right? But we only need the vertical component. Okay. So what we need to do now is just from these forces, just take the vertical component, sum them up, and then that's going to be the cumulative forces acting on kind of the particle, say on the other side of Newton's law. Okay. So let's see what those look like. So we're written out, right? Well, how do you take the vertical component of a vector? Well, that's just, right, kind of the magnitude of the vector times kind of the angle that vector makes with the x-axis. So I can draw it over here. Right, so if this is the vector, we'll draw it with vector notation, t of xt. Okay, so this is the x-axis, y-axis. This angle here is going to be theta of xt. Okay. The vertical component, so let's start with, okay, so this horizontal component is going to be the magnitude of that vector times cosine of the angle that vector makes with the x-axis. Otherwise, we have, right, the second piece, which is going to be the horizontal component, e of xt times, so the horizontal or the vertical component is going to be sine of that angle. Okay. So what we need to do now is, right, so here's a picture from before. So what we need to do now is, right, for each of these vectors, and so technically this should be that vector, but for each of these vectors, what we need to do is associate some sort of angle right, for these vectors to have relative to the horizon. And then once we have that angle, then we can kind of go in and just recover that vertical component. Okay, so what I'm going to do is I'm going to zoom in here, remove that. So what we're going to do is we're going to copy, right? So down here we have this x-axis, right? This is our horizontal. So what we're going to do is just say, well, let's take a copy of that right here. Okay, and so then that's going to be kind of our 0 angle. And so then with our coordinate system such that the origin is right there, the angle that this vector makes, this is going to be theta of x plus delta x comma t. Okay. So this is the angle that this vector is making relative to the horizontal. So, right, the vertical component here this is going to be, so the magnitude of the vector at the x coordinate, x plus delta x at time t, times sine of the angle it makes at that x coordinate. Okay. So this quantity right here, this is this vertical component of that tension force, which is going to be acting on the vertical motion for this particle. Okay. Okay, and so then we can do the same thing over here. And there are two ways to kind of go about this one. So what I'm going to do is I'm going to move this vector down a little bit so we can draw our copy of the horizontal again. Okay. And so here what we're going to do is we're going to say, well, okay, right, when we computed the angle for this vector, right, this was pointing along there. So one way we can kind of make sense of this is say, okay, well, take, right, this force acting here, right, that's pulling in the direction of this. This force is exactly minus this force up here. So one thing we can do is say, well, okay, draw this force. Take this vertical component, right? So here, this angle is theta of xt. This force is going to be minus this. And so the vertical component here, so I'll say vertical component coming from here, this is going to be minus t of xt sine of theta xt. Okay. So that's one way of seeing it. You can say, well, right, take the vertical component of this and then flip the sign. Another way you could see this is, well, what angle does this vector make? That's going to be this angle plus pi radians. So the vertical component technically is t of xt times sine of theta xt plus pi. Right, so this we're saying, take this angle, add pi, you get this vector, and then take the vertical component. But what you can then do is say, well, right, what are our trig identities? Sine of an angle plus pi is going to be minus sine of the angle. So these agree. Okay. Okay. But the point of all of this is saying, right, well, we have these tension forces acting on these particles. What are the vertical components? Kind of the vertical component coming from, you know, the right endpoint, that's going to be, right, the magnitude of the tension, t of x plus delta x come t, times sine of the angle. the contribution coming from the left endpoint is going to be almost the same thing, except now we have a minus sign here. And otherwise, it's, yeah, so it's minus t of xt sine of theta xt. Okay. Okay, so these are the forces acting on the string. So in F equals ma, right, from Newton's law, these two things, add them together, that's going to be your capital F. And of course, if you have gravity and any other forces, you're also going to add those to this capital F. Okay, so let's see how all that put together looks. Right, so right, so for kind of this, you know, these particles, these thin segments, what do we get? Well, on this on the left-hand side as written, right, this is our mass, this is our acceleration. And then all of this, let me change the color. All of this over here, this is our force, right? So this is the force that we're getting from tension at the right end of the string. This is the force that we're getting from tension on the left end of that string segment. And then this is going to be a black box kind of source term for anything else, okay? So if we have gravity involved, that would be added here. Okay, that would be incorporated in this function Q. And one other thing to note is how we've written things, right? Kind of the function Q that we're using, we're assuming that Q has units. Let's see, so this is going to be, so Q is going to have the same units as acceleration, right? Because we can see this quantity right here, this is exactly mass, right? So whatever units we have on the left-hand side, we should also have on the right-hand side. So Q is going to have units of acceleration, which is what? Length squared divided by time squared, or no, length, sorry. Length divided by time squared. So we're taking 2 time derivatives. Okay. Great. So this is Newton's law with all the pieces that we've kind of gotten together, plugged in. And so now what we can do is say, well, right, this equation depended on kind of the length of this infinitesimal string segment, right? And so we could say, well, you know, what if we take that length to go to 0? What if instead of having a sequence of beads, right, what if we fill in the string with a bunch of beads or particles? So what we're going to do, divide by delta x, and then take a limit. So delta x goes to the other side. Over here, so I can write this intermediate step. So we're going to have something like rho 0 d squared u dt squared. This is going to be t of x plus delta xt sine of theta x plus delta x t. Move that. So I'll move this over here. So this is this first term. We're subtracting off this term. So we're going to get a minus t of xt sine of theta xt. And then we're dividing all of this by delta x. So then that's going to get us delta x down there. And then we have a plus rho 0 q. Okay. So this is what we get, right, by taking this and dividing by delta x. And so here, right, the only thing that's going to be affected as delta x goes to 0 is this expression. And we recognize this as being the x derivative of t of xt sine of theta xt, right? Because we're taking a small increment in delta x, subtracting off, right, where we were at x, and then dividing by delta x. So divide by delta x, take the limit as x goes to 0. We're going to end up with this expression here, right? So rho of x, or rho 0 of x times d squared u dt squared is equal to d dx of the vertical component of the tension plus this rho of x q of x t. Okay. So far, this is where we're at. We're almost there. Okay. We have two time derivatives here. We have this rho naught q of x. Well, that's great. The thing that would be better is if instead of this t of xt sine of theta xt, we could express this term in here in terms of the height of our string u. Okay. So that's going to be our next step. Translating this expression right here in terms of u. And so then we should end up with something like t of xt times du dx. That's going to go in there, and then we're going to have the wave equation that that we've been looking for. Okay. So how do we do that? So the observation really is that, well, what is the slope of the string at any given point? That's the tangent that the angle, or tangent of the angle of the string, which for small enough theta is going to be approximately sine of theta. Okay, and so drawing a picture, so that's our horizontal. This is a tiny segment of string. If we take, right, so this tangent vector right here, this is exactly du dx, right? Because we're asking how does the height change as we go in the x direction? Well, what is kind of the slope of this vector here? Take the angle this vector makes with the horizon. The slope of that line is going to be tangent of that angle. So, of course, this is all kind of approximately. And then, so let's see. So the slope du dx is going to be approximately tangent of theta at that point. What is tangent? Well, tangent is sine of theta over cosine of theta, right? So then we could say, well, for theta small, cosine of theta is approximately 1. So then sine of theta over cosine theta is approximately sine of theta. Okay. So you might be saying, well, there are a lot of assumptions. All of this is kind of small. If, right, cosine of theta is approximately 1, then isn't sine of theta approximately 0? Technically, well, right, yes, but sine of theta for theta small is approximately just theta. So that's another, I don't know, approximation you could use or try to make sense of. You could also say, I don't know, there's a lot you could say. This is very much like a physicist's approximation and derivation, which you may be comfortable with, you may not be comfortable with, but this is sort of the hand waving that we'll be doing to get the wave equation. Okay, so with all of that said, right, what we're going to do is use this approximation, right, where the slope du dx, this tangent vector, kind of, or the slope of the string at that point, that's approximately sine of theta. Okay, so for our purposes, that means that whenever we see a sine of theta, we can approximate it with a du dx. Okay, so going back one slide, right, so this was the expression that we ended up with. So with all that said, what we're going to do is take the sine of theta and then plug in a du dx there, and using this very hand wavy approximation. And so then what that gives is this expression, which is the form of the wave equation that that we really want. So, right, what is the motion of a string, right? How does the height change in time? It's governed by this, right? So mass density times the acceleration of the string at that point is spatial derivative of the magnitude of the tension times the slope of the height, plus some other kind of black box term that just takes care of all the other forces you may feel. And so we can also write it by kind of suppressing the arguments. And so this is kind of a slightly cleaner way of writing this, where it's understood that rho zero just depends on x. This, and this all depend on x and t. Okay, but this is a wave equation. This one right here, coming from kind of Newton's law and some of these approximations for segments of the string. Okay, cool. So what we can do is kind of make a few other approximations just to see what forms or what other ways we can write this wave equation in. And so one series of simplifications we can do is say, well, if there are no external forces, or if there are, but kind of properties of the string and the scale that we're working at, these forces are negligible, so that effectively they're zero. So if we have no external forces and the mass density is constant and the tension in the string is constant, and so the fact that the tension in the string is constant, this is a property of the string that is called kind of the string being perfectly elastic, which means in practice that the magnitude of this tension force only depends on kind of local properties of the string. So you can get into kind of some of the physical reasoning and whatever. For us, we're just treating it as another function, another property of the string. And so for us, what we can do is say, well, assume that mass density and kind of the tension felt in the string, these are both constant throughout the string. All right, question is, what becomes of the wave equation? So this is the full wave equation, right? If Q is zero, this term goes away. If T is constant, then we can pull it out of that derivative. And so then we're left with this thing right here. And then what we can do is, well, divide by rho zero. And then we're going to get this expression where this quantity c squared, this is exactly T0 over rho zero. Okay, so this is another way that we can write the wave equation for a lot of practical purposes, right? If we're just looking for solutions and kind of qualitative behavior of solutions, this is a lot easier to solve than this. And kind of all the fundamental behavior that we'd like to explore and kind of see in some of these solutions is going to be encapsulated in this. One question that always comes up is, well, why do we write it as c squared and not just c? It's a valid question. Quick answer is, right, well, if we go through and kind of look at what the units of this expression are, turns out that the units are velocity squared. Okay, and this is a homework assignment as to kind of why this is the case, but there is a good reason as to why we write this as a quantity squared and not just a quantity. Okay? Yeah, so that's the wave equation coming from physical principles. And the next few videos, we'll look at first some other sorts of boundary conditions, some interesting sort of boundary conditions we can impose on strings, and then actually later on solve this equation and construct solutions.